Hello and welcome again. Today I'm going to talk about special valves in HVAC and their functions, and I'm going to talk in this video about PICV, and in the next video I will talk about DPCV as well. But before we begin, as per your informations, does PICV acting like a balancing valve? Here are the subjects what we are going to talk about them today. We will talk about definition of PICV, variable flow systems used PICV, where we use PICV, in the FCUs, in the AHUs, in the chilled water pump, plate heat exchangers, variable speed chillers, fixed speed chillers, and finally in the chilled beam. What is a PICV? A PICV is a valve that can be fitted in heating and chilled water systems to provide flow control, enabling modulating control of heating, cooling outputs. Flow regulation, enabling flow rates to be set at their specified design values. Differential pressure control, ensuring a constant differential pressure across control valves regardless of changes in pump speed or valve closures elsewhere in the system. This means that each PICV replaces up to 3 separate valves that would otherwise be required: a regulating valve, 2-port control valve, plus a differential pressure control valve. Pressure independent control valve for variable flow systems. Here is a pressure independent PICV valve, and this is an animation how it is controlling the flow of chilled water and how it is maintain the pressure difference as well the temperature fluctuatings. The pressure independent control valve PICV is a valve comprising an automatic flow rate regulator and a control valve with actuator. The valve can adjust the flow rate and keep it constant in the pressure of changing differential pressure conditions of the circuit. Flow rate is adjusted in 2 different ways: manually and on the automatic flow rate regulator to restrict the maximum value, automatically by the control valve in combination with proportional 0 to 10 volt or on-off actuator in accordance with the thermal load requirement of the circuit of the system to be controlled. The pressure independent control valve PICV is supplied complete with connections for upstream and downstream pressure test ports for checking of operating conditions. The valve can be used in heating and air conditioning systems. This is the operating principle of the PICV. The pressure independent control valve PICV is designed to regulate a flow of fluid by an actuated 2-port control valve that varies the flow through a terminal unit, a differential pressure control regulator that maintains the constant differential pressure across the control valve, thereby ensuring the maximum set design flow rate cannot be exceeded. The valve construction is shown in the schematic diagram, where P1 is the upstream pressure, P2 intermediate pressure, P3 downstream pressure, delta P for total valve equal to P1 minus P2. Valve B regulates flow rate G by changing the flow path cross section. The change in flow path cross section determines the hydraulic coefficient value kV of the regulating valve B, which remains constant at manually preset value, the value determined by the actuator's regulating action. Device A regulates delta P1, which is P2 minus P3, and keeps it constant across the valve B by means of an automatic action balancing between the force generated by the differential pressure and the internal opposing spring. If P2 minus P3 increases, the internal delta P regulator reacts to close the valve and maintain P2 minus P3 constant. In these conditions, the flow rate will remain constant. Where we have to use this PICV, and what are the applications, functions, benefits, and considerations. Number one, we can use it in the fan coil unit with PICV control. The function: the room temperature is controlled by a controller connected to the PICV actuator. The control can either be modulating or on-off, or depending on the system layout. The benefits: the PICV ensures balancing of the flow and eliminates the use of both static balancing valves and differential pressure control valves, also to provide stable operating conditions and so consistent control at each terminal load. Simple installation, as only the PICV is required, with no need of additional pressure or flow balancing valves. Low total pressures loss in the system due to simple design. The flow can be set directly on the PICV without the need of a manometer or commissioning unit. The differential pressure only needs to be checked at the PICV placed at the index point or at the end of every branch. Considerations: a metering station can be placed on the branch if additional flow verification is required by the witnessing authority. The index valve will in applications such as this with identical design and coil performance be the one furthest from the pump, but it can be elsewhere in other layouts. In theory, PT plugs are only needed in the index PICV, but for commissioning and diagnostic purposes, it can be useful to have PT plugs on every valve. Here is the schematic diagram for the PICV and the fan coil units applications. Air handling units with PICV direct control. The function: the air temperature of the air handling unit is controlled by a sensor in the outlet. When the control system calls for higher or lower temperature on the air outlet, the PICV opens or closes to increase or decrease the flow through the coil. The power output from the coil follows a parabolic curve where often an EQ percent valve/actuator characteristic is chosen to have a direct relation between the input control signal and power input. The benefits: the PICV ensures balancing of primary flow and eliminates the use of both static balancing valves and differential pressure control valves. Simple application, as only a PICV is required to control flow, temperature, and differential pressure. Considerations: at part load, the flow through the coil can be low, leading to laminar flow and reducing the power output. Larger coil can have different temperatures in different areas of the coil, making precise temperature control difficult. A metering station can be installed if additional flow verification is required. And this is the schematic of this case. In air handling units with PICV injection circuit control. The function: the air temperature of the air handling unit is controlled by a sensor in the outlet. The secondary side of the injection circuit circulates a constant flow through the coil, maintaining a uniform temperature throughout the entire coil. When the control system calls for higher or lower temperature on the air outlet, the PICV valve opens or closes to allow heating or cooling water from the primary side of the injection circuit to enter the secondary side. The temperature in the coil then changes, giving an almost direct relation between the temperature in the coil and power output from the coil. The benefits: the PICV ensures balancing of the primary flow and eliminates the use of both static balancing valves and differential pressure control valves. AHU with a large coil area have a uniform temperature in all parts of the coil, providing a precise temperature control. Direct relation between coil temperature and power output. Considerations: requires a small circulation pump on the secondary side of the injection circuit. A metering station can be installed if additional flow verification is required. And here is the schematic diagram for this type of air handling unit. Number 4, chilled water pump with PICV control. The function: the PICV valve is typically installed at the terminal unit, replacing the traditional two-port control valve, commissioning valve, and DPCV, removing the need for additional system balancing valves and DPCVs. The PICV valve will operate effectively at all differential pressures between the minimum and maximum rating for the valve. Pump speed must be controlled to maintain a minimum pressure differential at a selected point or points in the system. The most energy efficient approach is to locate a differential pressure sensor across or close to the index sub-branch. When all the PICV valves are approaching their closed positions, there needs to be a path open for flow to prevent the pump operating against a closed system. An effective end-of-line relief and low-flow pump protection strategy is therefore essential to prevent dead legs, poor temperature response, poor return temperature control, and pipe wall vibration. Benefits: in minimum flow circulation and variable flow systems that prevent the pump from operating against a closed system and maximize the energy saving potential available from well-designed variable flow system. Low flow pump protection: install an externally adjustable constant flow valve CFV as an end-of-line bypass valve on each branch of terminal units to avoid dead legs. Circulate chemicals and ensure good temperature response. Considerations: install PICVs on the terminal unit to provide flow temperature and pressure control in variable flow systems with a constant flow rate CFV for end-of-line bypass. Address the end-of-line bypass and low-flow pump protection strategies separately. And this is the schematic for this case. Number 5, plate heat exchanger with PICV control. Function: the primary function of the PICV is to control the water inlet temperature on the secondary side. To secure the water outlet temperature on the primary side of sensor is placed here. The balance of the full modulating control on the primary side is made by PICV with a modulating actuator. When the controller calls for higher or lower temperature on the water inlet on the secondary side, the PICV valve opens or closes to allow heating or cooling water from the primary side to enter the plate heat exchanger. The temperature on the secondary side then changes to the desired temperature. Benefits: the PICV ensures balancing of the primary flow and eliminates the use of both static balancing valves and differential pressure control valves. Formulating with an authority of 1 for the plate heat exchanger control. Return temperature on the primary side is secured. Secondary pump is switched off when no demand. Considerations: minimum differential pressure required for the PICV must be available at design flow. And this is the schematic for this case. Variable speed chillers. Plant room with PICV control. Functions. The function of this PICV: the variable speed chillers are connected to the controller, which controls the flow through each chiller by the PICV. The controller measures the inlet and outlet temperature to minimize delta T and regulate the variable speed pump to maintain the required pump pressure. For optimal chiller efficiency, the use of multiple chillers at lower capacity or cascade control at park load shall be selected, depending on the chiller design and control philosophy. Benefits: the PICV ensures balancing of the flow and eliminates the use of both static balancing valves and differential pressure control valves. Simple installation, as only the PICV is required with no need for additional pressure or flow balancing valves. Low total pressure loss in the system due to simple design. The flow can be set directly on the PICV without the need of a manometer or commissioning unit. The differential pressure only needs to be checked at the PICV to set the required flow. Considerations: a metering station can be placed on main line if additional flow verification is required by the witnessing authority. A minimum bypass flow can be required by the chiller to secure instant cooling or circulating of chemicals in the system. This should be placed at the most appropriate place in the system. And here is the schematic for this case. Fixed speed chillers, plant room with PICV. The function: the fixed speed chillers are connected to the controller with opens, which opens and closes the flow through each chiller by turning the PICV on and off. The controller measures the inlet and outlet temperature to minimize delta T and regulate the variable speed pump to maintain the required pump pressure. For optimal chiller efficiency, the use of cascade control is recommended. The benefits: the PICV ensures balancing of the flow and eliminates the use of both static balancing valves and differential pressure control valves. Simple installation, as only the PICV required with no need for additional pressure or flow balancing valves. Low total pressure loss in the system due to simple design. The flow can be set directly on the PICV without the need of a manometer or commissioning unit. The differential pressure only needs to be checked at the PICV to set the required flow. Considerations: metering station can be placed on the main line if additional flow verification is required by the witnessing authority. A minimum bypass flow control by a dynamic flow limiter is required by the chiller to avoid freezing, as they are running at full capacity when switched off on. And this is the schematic for this case. Chilled beam with PICV control. Function: the room temperature is controlled by a controller connected to the PICV actuator. The control can either be modulating or on-off depending on the system layout. On-off control is often selected on passive chill beam to avoid laminar flow, which lower the cooling transfer from the water to the coil. Benefits: the PICV ensures balancing of the flow and eliminates the use of both static balancing valves and differential pressure control valves. Simple installation, as only the PICV is required with no need of additional pressure of flow balancing valves. Low total pressure loss in the system due to simple design. The flow can be set directly on the PICV without the need of a manometer or a commissioning unit. The differential pressure only needs to be checked at the PICV placed at the index point or at the end of every branch. Considerations: a metering station can be placed on the branch if additional flow verification is required by the witness authority. The index valve will, in applications such as this with identical design and coil performance, be the one furthest from the pump, but it can be elsewhere in the other layouts. In theory, PT plugs are only needed on the index PICV, but for commissioning and diagnostic purposes it can be useful to have PT plugs in every valve. And here is the schematic for this.